So we spent the last couple lessons talking about Unix and Linux environments. We talked about networks and computers and servers. And finally, we talked about forges so that we had these three places: our local machine, our remote machine, and our third space where we could actually collaborate with people. But maybe today we're not really satisfied anymore with just using the programs that other people have written for us. Today we want to return to the idea of how do we actually write programs in this Unix environment, start the programs, stop the programs, and then develop them further. So with that in mind, we're going to start pretty much where you might expect us to, by opening a terminal. So far we've seen a lot of different programs, like we've seen ls, we've seen this program called touch. We've seen that when we run certain programs, they change how our operating system behaves. We've even seen a little bit of programs that involve user interaction, such as nano, which we can launch given a file name. We can write some stuff inside of the file, and then we can use this to Control X, write that information out, and then have something slightly different inside of the file. So everything we've dealt with so far, such as the touch command, the nano command, and the cat command, we'll call them kind of these simple programs. But that brings us to something else, which is this thing called Python. So if touch creates a file, nano edits a file, and cat concatenates the contents of a file out to the terminal, what does Python do? So Python is something called an interpreter. What Python does is it takes a description of a program and it actually interprets that and runs it on our computer. So if I do python3 always.py, oh, well, what's happening? It looks like I can press enter. I can, okay, well, backspace doesn't work. Nothing else is working on my computer. So what's happening? Well, while true actually kind of forms the backbone of a lot of the user interactions that we're going to use for the rest of the semester, we want to start some kind of program that may potentially run forever and is constantly waiting on the user for some kind of interaction. So this is really powerful, but this is also potentially annoying. So the next thing that we want to learn about is the SIGINT, or the interrupt signal, which we can use with Control C. So this triggers something called a keyboard interrupt, or a interrupt SIGINT signal, which will tell Python, well, from the perspective of the operating system sends a signal to Python, which tells it to shut down and return control back to me so that I can start typing and modify things and do ls and run all my other programs back again. So as long as you're comfortable with the idea that we can start programs, we can maybe wait for them to complete, and we can interrupt them if they're misbehaving, you basically have most of the concepts that we're going to need for the rest of the semester. So I'm going to remove this always.py because we're not going to really need it anymore. And let's talk a little bit about where we're going to go next. So programming languages are are also programs. The name for what you've actually been interacting with here is called a REPL. So these can also be a really good, useful way to actually debug things. So in the same way that I could start a program inside of a file, I can also interact with Python from the REPL right here, or the read, evaluate, print loop. So right now it is waiting for me to actually interact with something inside of Python. So if I go while true, pass, notice this is going to be doing pretty much exactly what we saw when we had always.py. I can still send the interrupt signal, but in this case it's going to take me back to a Python prompt where it is going to wait for me to just keep giving Python instructions. So similar to what we saw earlier, we can send the keyboard interrupt, but it will instead bring us back to a Python prompt. There's two ways that we can actually get out of this, which would be either to do the Control D, which is I think the end of terminal or the end of transmission signal, or if we're still in Python, we could also just type the word exit, open close parentheses, in order to exit out of Python itself. So the next step, I think, is designing or writing programs. So programming languages are built from about 5 essential components. We have things like variables, which we can use to store data and use it later. We have things like conditionals, which let us choose different behaviors. We have repetition, we have abstraction with functions, and we have the application of those functions in order to invoke them and turn them into some kind of result. So really what we want to do, though, is we want to take some of the essential components and then we want to build bigger and better systems out of them. Now, one of the ways that I tend to like to do this is with the scaffolding of the function design recipe. So you can pause here if you want to read this, or you can read it directly in the book. So what I will do is I will highlight some of the big points, and then I actually want to apply this and show you how I might use this to approach a rock, paper, scissors game. So step one in this workflow is to go from the problem analysis to the data definitions. And so I'll clear my screen, give us a little bit of room to talk about stuff. And in rock, paper, scissors, let's kind of describe the game at a high level. So we have 1, 2, 3 things, which we will call the rock, the paper, and the scissors. And in rock, paper, scissors, we say that paper will wrap rock. We will say that rock will crush the scissors. And we will say that the scissors will cut the paper. So this image right here is what I'd say is actually the core data that is needed to represent rock, paper, scissors. So identify the information that must be represented and how it is represented in the chosen programming language. Formulate data definitions and illustrate them with examples. So what I would argue here is that the core problem that we're trying to solve is we're really trying to figure out who is the winner, or what combination of two things determines which person wins and which person loses. So maybe I can just think of these as just being strings. So we will have two players, which maybe we'll say is the human player, which let's imagine the human chooses rock. And let's imagine that we have someone else, which is maybe going to be the computer program. And let's say that the computer chooses scissors. So in order to decide the winner, what we have is we are looking at a specific edge in this graph of nodes. In this specific case, we can look at this one and see that the human chose rock and the computer chose scissors. So therefore, because this is a node this is an edge in the graph, we can be sure that the human was the winner in this case. Let's kind of play out a different example. So what if we were in an edge that doesn't exist in the graph? So what if we had a situation where the computer, we'll say C, chose paper and the human chose rock? Well, if we have an ordering over those two things, notice that rock and paper is not necessarily one that is in the graph. We do not have an edge from this thing to this thing. So this is hinting at the core thing that we need to represent, which we'll say is the second step, the signature, the purpose statement in the header. So state the kind of data the desired function consumes and produces. Formulate a concise answer to the question of what the function consumes. Define a stub that lives up to the signature. So if I want to define this, what we want to represent is something like, does something beat something else? So maybe we'll say that this is beats. So does, actually let me get a little bit better room. So the beats function determines whether the human player beats the computer player. And we may think of these two things take a string. So the human will take a string. The computer player will be a string. And what we want to decide is, does human beat the computer? Does human beat the computer basically means that we are returning true or false. So this function will have a signature that probably looks like, takes a human, which is a string, it takes a computer, which is also a string, and produces a Boolean output. Okay, so there's a lot more that we probably could do, and there's probably a lot of other stuff that we could apply some of these same pieces to, but here's a core argument that I'm going to make in a bit. This right here is the core problem that you're trying to solve in rock, paper, scissors. Figuring out what is the human choice, figuring out what is the computer choice, and then displaying things like winners or losers, and whether or not and whether the human beat the computer, whether it was a tie, etc. Most of that is just going to turn into input and output control. As long as you can figure out this core problem, which is the core data in the core data structure needed to represent the actual problem, most of the other stuff will kind of fall into place. So let's kind of wrap this up. Let's scroll down and talk about some of the important points. We're going to need some subset of Python. We're probably going to need something like input. We're probably going to need some kind of random choice and behavior. And we probably will need something that deals with the input-output control, such as saying that like canon is not a valid choice in rock, paper, scissors. So we do have a template to get you started with today. If we go to GitHub, you should see that you have a repository out here. In my case, well, my name is Hayes All. I'm going to look for my Hayes All i211, nope, my Hayes All i211 starter. Recall that we can pull the web address out of this, and we're going to clone the repository and start working inside of it. So I don't really have anything just yet, so I'm going to create an i211 directory, cd inside of it, maybe git clone, then drop the URL in there. Once we have that cloned, we will cd inside of that, inspect that we have a few of the files, and then finally code space period 321 is going to open it up in Visual Studio Code. So we haven't talked a ton about Visual Studio Code just yet, so I'll give you a quick tour. First things first, I actually find this welcome page really annoying, so I'm going to uncheck this box so that it's no longer going to show this every time I open it up. I'm going to close that tab, and then I'm going to do Control B. There's a few ways you can approach this. Notice that there's this thing called the Explorer view at the top. I can click this, I can unclick this. If you do want to get used to the shortcuts, Control B is also a way to represent that. And then inside of here, I have access to all my files that I just cloned from GitHub. So here's the README, here's the RPS where we can actually work on stuff. There's a test RPS, which we're going to talk about probably next session. And inside of this file, I pretty much have access to the same way that I was editing files inside of Nano. So if I was to implement this isValid function, well, let's just do this one way for now. So let's return like if raw is equal to rock, then maybe we consider that to be a valid choice. So I can open up an integrated terminal with control backtick. Let's repeat that one more time, control backtick, and backtick is this character, control backtick, 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 backtick. A backtick character is this thing, which is usually, if this is your escape key on your keyboard, it's usually going to be right here at the top left corner of your screen. So control backtick will open up the integrated terminal. Notice that in here, I can also type commands pretty much exactly like I would have back in my regular Windows terminal. And from here, I can also do things like launching programs. So I can start up RPS. At the moment, this doesn't really do anything all that interesting, but if I were to say inside of RPS right here, and then try running the file again, then it would say that I am inside of RPS right here. So here's what I want to see you do for your next goal. We have some instructions for how to get started in rock, paper, scissors with the subset of Python you might need. I want you to think about how do I actually implement rock, paper, scissors. So you're going to ask the user to choose an option, possibly multiple times if they have some typos. In the event of those problems, you will send an explanation to standard error. You will choose a random action for the computer, and will you display the winner? Was it a human, was it a computer, or actually was it a tie as well? So starting from this, I want you to fill in the gaps of what should go in some of these places in order to scaffold out an entire implementation with incremental development, where incremental development is this idea that you can maybe add a little bit of code along the way, see whether or not your ideas are correct, and then eventually get towards something that's a workable final solution. And a complete program of rock, paper, scissors might look kind of like this, where the user can invoke rps.py at the terminal. That will ask them to give some new information. If they give some bad information, like trying to specify canon, then you will say unknown, maybe try again. But if they are successful, like the human chooses rock, the computer chooses paper, then it'll give the feedback that the computer wins. So in just a moment, I am going to implement a solution, but I really, really want you to pause the video here because the only way that you will actually learn is by trying. So if this is easy, great. If this is hard, maybe try it out a couple times. Eventually, once you have a workable solution, then take a look at mine. There's really no excuse if you didn't do it because the only way to actually learn is by trying. So seriously, pause the video here, and in just a moment, I'm going to start implementing this and kind of talk through my process of how I would actually go about building this. All right, so if you're hearing my voice right now, I'm going to assume that you have a working copy of RPS, or at least something that's really close, and you want to start getting a little bit of feedback onto how are you going to make this a little bit better. So I'll kind of walk through some of my ideas for how I would approach this. So let's kind of drop this out, get me back to a fresh state. Drop that, drop that. Actually, even easier, git restore space period. We'll get things back to a good working order that we started with. Okay, so this is pretty much going to be exactly the same as it works. Where do I want to go next? Okay, so let me kind of scroll up to some of these pieces. So we think we're going to need something like input control. So let's just kind of start scaffolding some of this stuff out. So I think inside of the main block, which I'll work inside of here for a little bit, we want to do something where we get information from the user. So maybe that'll be something like the human input. Then we're going to need something to get the computer input. So computer, let's just kind of keep scaffolding this out. The computer is going to be a random choice. Then we need to do something about figuring out who is the winner. So this was that thing that I mentioned earlier inside of our function design recipe, where the key thing to implement is the idea of what beats what. So I think I was sketching this out as something like the beats function. And the beats will take two players. It will take a human, which we said was going to be a string. It will take a computer, which we also said was a string. And we want to return like, does X beat Y? Or does the human beat the computer? So we said this was going to be a Boolean structured output. Now, what are some examples of how we actually want to use this? So we think that when we use this function, we will have something like, does rock beat scissors? And this thing should return true. We may say, does the scissors beat paper? Well, scissors does also beat paper, but what about the inverse? Does paper beat scissors? Oh no, that should be false. Okay, so how do we start creating these into a function that will always return true or always return false? Maybe our first inclination is to think of this as an if statement. So if human equals rock and computer equals scissors, we want to return true. Elif human is equal to scissors and computer is equal to paper, return true. Oh boy. Okay, well this is about to get really, really annoying if I have to do it this way. So this is maybe you're starting to see that there's a slightly easier way we can represent this, because I think we said earlier there's a set of things that will be true, and everything that is not a member of this set will be false. So what if I kind of represent it like that? So let's think of, we have a set of things that are correct. So let's call this maybe the winning moves. So winning moves is three possible things. So we could say rock beats scissors. We could say that scissors beats paper. And we can say that paper beats rock. So we have three winning moves. And really the way that we decide whether or not something beats something is if human computer is in the winning moves, then we return true. Human computer, we return true, else we return false. Okay, so this actually might be a functional solution, which this is a good time to go into, what is it, step 6 of our function design recipe. Let's see, nope, I just lost the page. There we go. So I think step 6, so let's kind of talk back through the function design recipe. We previously did the whole analysis. We wrote a header. So actually, let's kind of refine this header real quick. So does human beat computer, question mark, because this is a predicate. We gave some functional examples. So notice we're going to draw a box around these. Our functional examples was what I was using to figure out like how I actually want to implement this. I sketched out a function template, and then we actually defined the function. So step 6, we'll talk about this a little bit more, but this is about testing. So we've implemented this function. So the next question is, does this function do what we expect it to? You might need to refine this a little bit, but for now, one way that we can test this is just by writing some code beneath this. So we think that rock should beat scissors. So what if I had some print statements right here? So does rock beat scissors? Does scissors beat paper? And finally, does paper, let's copy this again, does paper beat scissors? So if our code is implemented correctly, this should output true, true, false. So let's see what happens when we actually run the code. Python 3 rps.py, true, true, false. So true, true, false is what we expected. That's what we got. So maybe we're pretty confident about the implementation of the beats function. Let me do one more step, which is to actually clean up this implementation a tiny bit. So these are, this isn't terribly important perhaps, but these are some little tricks that you tend to notice a little bit more over time. So we have an if statement that always returns either true or false, which means that we could actually inline this into a single return statement. So let's transform this. So instead of returning that, let's take this computer apart, and we can say if this is in winning moves, that's the same as this block that was returning true in one block of the if statement, false otherwise. But notice there's something else right here. So do we really need this variable that's only used in one situation? Well, maybe. It's a little bit of a kind of a personal preference though, but I tend to like inlining these into a single statement. So now we've transformed the beats function from a about 5 lines of code up into something like this, where you simply return whether the human computer is in the set of winning options, which is functionally identical. So previously we did true, true, false. Now if we run this again, we still get true, true, false. So cool. That means that we're probably in a pretty good state at the moment. What is a good next step for us? Okay. Well, let's see. We have something that's kind of getting the human choice. We have something that's getting the computer choice. So maybe we can just try to see whether the human beats the computer. So maybe we can print the human, maybe we can print out the computer, and that we can print, does the human beat the computer? So try that again. Maybe pause here, try to kind of think about that. So Python rps.py, try again, Python 3 rps.py. Okay, so here I am on line 26. I'm going to choose rock. Ooh, interesting. Okay, so zoom in on that. So I chose rock, the computer also chose rock, and it was a false outcome. So human did not beat computer, but in fact there was a tie. Okay, so I think we're getting a little bit closer to a solution. So here's the first thing we need to think about. We need some kind of way to represent, is it a tie? So we can figure out if it's a tie. So let's say if human is equal to the computer, maybe we'll print out it's a tie. Okay, well this is the first block of our if statement. The next choice is, does the human beat the computer? Okay, cool. So we're getting closer. So now we can invoke that beats function. We can say if the human beats the computer, we can say print human1 exclamation point. Otherwise, else, we will print computer1. Maybe for good measure, let's also print something like computer chose, and then this is the choice that the computer put inside of it with an F string. So do a tiny bit of cleanup, see what was the final result. What happens when we run rps.py now? Okay, well, it's asking me to choose something. Let's choose paper this time. Okay, well, human chose paper, computer chose rock. Oh, therefore I won. Awesome. Okay, so we're really close on most of the things. We have a function that that determines whether the human beats the computer. We have a lot of stuff written in the main module at the moment, and we're still not using this isValid function. So let's kind of remind ourselves, what is the goal of that isValid function, and what are we actually trying to do? Okay, well, we need some kind of way to represent like when things are correct. So we shouldn't be able to do canon right here, because canon entering our program is going to cause some, well, maybe unexpected behavior. So let's kind of refine this. So we have this standard error, and we know that we can use some kind of print statement with the standard error in order to point to that problem. So I bet we want to represent isValid in terms of, let's see, is this a valid choice or not, question mark. So we want to represent some ideas where isValid canon is not a valid choice, but we want to say that rock is a valid choice. And similarly, we want to say like paper is a valid choice. So I think this should be pretty straightforward. Let's kind of do that same pattern where I think a moment ago I said maybe if raw is equal to rock, we return true. we return true. We could say if raw is equal to paper, we could return true. We could say if raw is equal to scissors, we return true. Otherwise, we return false. Okay, so we have a big tower of if statements. This is another one of those things that I've been programming for a little while. I tend not to really like seeing these because there's really a much easier way we can write this, which maybe kind of parallels some of the things we see down here. So what if we just say return the raw value in rock, paper, or scissors? Functionally identical to these giant tower of if statements down here, which actually, let's kind of see both. So, so we've sketched out the way that the goal of this function. We've turned those into some assumptions about what the inputs and outputs should look like. Let's kind of jump down to step 6, which is to actually test this function. So let's drop in some of these examples. So let's print out, is cannon a valid choice? We could say, is rock a valid choice? And we could say, print, is valid paper a valid choice? So if our assumptions are correct, we should see false, true, true right here. So backtick, open the terminal, Python 3 rps.py, and the first 3 lines are false, true, true. So maybe we're pretty confident that this return raw is the same. I'm going to comment that out for just a moment and see, do we still get the same solution of false, true, true if we use the tower of if statements? Yep, false, true, true. So maybe we can conclude that these two things appear to be mostly the same, and we can actually just stick with a simpler solution. Okay, cool. So we're getting somewhere. So now we have an is valid function, but notice that, let's see, Control F is valid. So we represent it in a few places, but we're not actually using it anywhere just yet. So let's jump back down to the main block. And here's where this idea is that we want to ask for human input until they give us something valid. Okay. Ask for human input until they give us something valid. Okay, so I've, again, kind of done this for a little bit. I bet it has something to do with some kind of while loop in order to wait for something to be true. Maybe we will put the human input inside of there. We will say something like, if the human input is valid, so if human is valid, we can break out of the while loop. Otherwise, we probably want to say something like, let's see, unknown value. Oh, cool. Okay, we can kind of copy and paste from here, and I like it when I can just kind of copy and paste and think through things. Okay, change this. Human choice is underlined with the squiggly because it's undefined. Let's put that in there. Okay, cool. So we might have a working solution now. So we are going to query human input until they give us something valid. We're going to see what the computer chose. Then we are going to determine the winner inside of here. Let's see what happens when we put all the pieces together. Python 3 rps.py. Okay, so I'm going to type scissors. Okay, computer also chose scissors and it's a tie. That looks good so far. Let's see if I do okay, unknown value, Let's see if I do some other stuff. Yep, all of these are unknown values, therefore all of these should be errors. Let's finally give it a real one for paper. And computer chose scissors, and the computer won. Okay, we are very close. Okay, so this is a good time. I think I have some pretty much working code, so this would be a good time to make a commit. So let's do git status. Let's say git add rps.py, git commit-m, and say add initial rps implementation. Close out the double quotes. Enter. Okay, so that created our first commit, and we have pretty much working code right here. So here's what I want to do next. I actually want to tidy this up, and I want to make things just a little bit, a little bit nicer for future Alexander. So there's really a few things that are happening inside of here, which I think we can give names to. So this first step is like, solicit human input, or maybe something like get human input, something like that. I feel like there's a name for this step right here. Similarly, right here, if we're doing something where we're soliciting the human input, we kind of have something that's similar like get computer input, something along these lines. I want to turn these two things into functions. So let's kind of pull these definitions out. So we think that there could be some kind of function called getHumanInput. So let's start defining that. And the goal of this is that we want to ask for user input until it is a valid choice. Okay, so this is a function that's going to take no input, but we want to eventually return a string out of it. So I'm going to do Control-X to drop that out of here, drop that right here, and then return the human value at the end, which means that now we can solicit human input by saying human is equal to getHumanInput. Okay, we're just kind of moving some code around and kind of organizing our ideas for later. Similarly, we can do the exact same thing with computer. So let's do something like define a new function called getComputerInput. Drop that down there, Control-X to cut that out. Jump back up here, define getComputerInput, which is very similar. It's also going to return a string, but instead of working through all of this while loop, we're pretty much just going to choose a random choice. So let's pull this out, drop it in here, and instead of just assigning it to a variable, let's return the choice at the end, and then we can assign the computer is equal to getting the computer input. This print statement is kind of representative of something happening inside of the computer input. So changed my mind. Maybe I will still do the variable inside of here that just assigns the computer to a choice and then just returns the computer choice at the end. Okay, cool. So this is a little bit out of personal preference, but part of the motivation of this is that I tend to like keeping my main blocks about as small as possible. So run the full program to get input and choose a winner. Okay. Let's do a little bit more tidying up. Okay, so asking the user, let's choose a random option for the computer player. Okay, so I've made a few different changes. Let's see what would be a good time. Kind of jump up to the very top, kind of scroll down to the bottom, maybe see if there's any other quick changes we can make just to tidy up the code. So I tend to like leaving 2 spaces between each of my functions. So 2 spaces, 2 spaces, 2 spaces. Again, kind of all out of personal preference. And I said something to the effect of, I want the main block to be as small as possible. Why is that? Well, we talked about a little bit about testing. So another way of thinking about this is that how would we know whether the computer input is working correctly? Well, let's imagine that maybe I've got a couple cursors, and this is another cool VS Code trick. So if I do Alt plus Control, drop down my mouse a couple times, now I have a lot of different cursors all happening at the same time. So let's see if we can just see what happens if we print out a lot of things. So paste that in there. And what happens if I just run the computer input quite a few times in a row? Well, if I run this, so Python 3, rps.py, okay, cool. So I can actually get a lot of information as to whether or not this function's working correctly. So the first time the computer chose paper, paper, scissors, scissors, scissors. Here's kind of the nice thing, which we'll talk about throughout the rest of the semester. The nice thing is that functions are easy to test. Usually they have a pretty simple input and a pretty simple output, so it's pretty easy to see that we can look at the result of running the function and see whether or not it's meeting our expectations. This thing, on the other hand, it's doing a lot of kind of complex behavior. It has to first get the human input, then get the computer input, then do a bunch of comparisons to see whether or not those two things are actually valid. So if we work at the level of functions and kind of break these behaviors down into concepts that we can name, such as getting the human input, getting the computer input, it kind of eliminates a lot of these needs for a bunch of extra commenting, and it makes it so that our programs are just significantly easier to test. But some of that will come down in personal preference, and those are concepts that we'll get some more practice with at the end. So let's do a quick get status, maybe say what is the difference between the previous state, and let's make a commit right here where we add everything to our staging area. So rps.py is now in our staging area. Let's make a commit where we say tidy up code and refactor. I don't quite know what refactoring is yet, but we're going to talk about this word a little bit later in the semester. So, and refactor into functions. Close out the commit, git status. We're 2 commits ahead of main. So let's finish this up by pushing everything back up to GitHub.